Welcome back. Unit 8, Chemical Equilibrium. The concept of chemical equilibrium. Chemical equilibrium is achieved when the rate of the forward reaction is equal to the rate of the backward reaction. There is no net change in the concentrations of the reactants and the products. So over time, let's say with A plus B is equals to C. So remember the left side, these are reactants. Reactants. Okay, let me reactants. And this side, the right side, is products. So now, over time, at first, the concentration of the reactants will be more at the beginning. Here, you can see it's more at the beginning. As the reaction occurs, this A and B will be depleted. So when the reaction is occurring, C will be formed. So the level of C at the beginning is 0, but when the reaction is occurring, the number of the concentration of C will increase until it reaches a stable level. So at this level, that's where we reach chemical equilibrium, because there is no more increase or a change in concentration of the reactants or the products. So that is the concept of equilibrium. So equilibrium constant. Equilibrium constant is defined as the product of the molar concentration of the products, which is each raised to the power equal to its stoichiometric coefficients, divided by the product of the molar of the reactants, each raised to the power of its stoichiometric coefficients. So basically, stoichiometric coefficient is constant at constant pressure. So the rate of forward reaction is equal to the rate of backward reaction. So at this, then we know that there is a balanced or a chemical equilibrium has been reached. So here, basically what we are saying, let's say we have what A. Okay, let me do it like this so that it will be clear. So we've got A plus B to form C and D. So here we are saying the coefficient are like that. So basically, you take the products, you put them on top. Products. So this is what we're trying to explain here. Products over, so in this case, we are taking C and D, which are these ones, raised to the power of the, so remember here we are taking the stoichiometric coefficients. But for reaction orders, these are experimentally calculated. But in this case, for equilibrium, we use the stoichiometric coefficient. So C and D, so we raise them to their power, which is the same for A and B. So remember, these are molar in concentration, the brackets. Then these are the reaction constants. These ones. So when these are combined, they form C, Kf over Kb. They form. So Kf is the rate constant of the forward reaction. Then Kb is for the backward reaction. So Kf, we just say equilibrium constant. It's just calculated that way. So usually they give you, but it's fine. Equilibrium constant, Kc, is only affected by temperature, not initial concentration of the reaction. So this one is temperature dependent, not concentration dependent. So that's why we were mentioning at constant temperature. If you change the temperature, it will affect the reaction rate. That's why the Kc, the equilibrium constant, will change. So basically, when it's a different temperature, the equilibrium positions may change. Maybe at a certain temperature, the equilibrium will happen here, and for this one, it might happen here. So it will affect the equilibrium constant. So that's why it is important to notice that we are dealing with constant temperature. Equilibrium constant can be simply expressed in terms of partial pressures of the reactants and the product. Then it can be denoted as Kp. So when you are using temperature, when you're using pressure, it becomes Kp, which means it's the equilibrium constant based on partial pressure. Then Kc is equilibrium constant based on the concentrations. So basically, this is something to know. So we can move on. So equilibrium constant. So this is the forward direction is from here to there. The backward direction is we are coming from here to there. So when you are doing the forward direction is like this, red, and the backward reverse. So sometimes they put R. Is this one. So basically, when you are writing out the Kc, it will be the concentration of this to the power 2 divided by n. Here is to the power 1, so you can just leave it like that. So this is how it is. It's simple, but you understand it more and much clearer when we do more practice questions and exam preparations, which is available on our website. More notes. Equilibria in which all reactants and products are in the same phase are called homogeneous equilibria, whilst equilibria in which one or more of the reactants are present in different phases are called heterogeneous equation. So we are homogeneous, which means we are on the same phase, which means all the products and the reactants are gases or a solid. So it's homogeneous. But if one of it is gas plus solid, then it forms a gas. So there are more than one states. You understand? So it becomes heterogeneous. Heterogeneous just means more than one phase. So that's what we are referring to. Okay. Pure liquids or solids are not included in the equilibria expression, although they must be present for the reaction to occur and reach equilibrium. So this is just a point to note. The magnitude of the equilibrium constant K indicates the extent to which a reaction will proceed. If K is greater than 1, it means the equilibrium concentration of the product is large. So basically, remember K, we are saying concentration of products over concentration of reactants. So it means if this one is big, if the reactants are big, then it means the value of K will be smaller. So it means the reactants are the concentration of the reactants. So it means the equilibrium concentration of product is large. When K is less than 1, it means the equilibrium concentration of reactants is large. So basically, when when the reactants concentration is large, which means your K will be smaller. So that's when it will be K. But when reactant concentration is smaller than the product, so K will be greater than 1. But if they reach at the same, maybe as what if it is the same, then it will be 1. K will be 1. So that's the simple answer. So Le Chatelier's principle. Le Chatelier's principle states that if a stress is placed on a system that is at equilibrium, the system will shift in such a way to relieve that stress. Stress on a system can be attributed to concentration of reactants or products, temperature of the system, pressure of the system. So Le Chatelier's principle is saying when a system is balanced, is at equilibrium, when a certain stress, which can be in the form of concentration, temperature, or pressure, comes to disturb that system, the system will react in such a way to relieve, which means to reduce that disturbance, so that equilibrium can be reached again. So that's what Le Chatelier's principle states. So in order to summarize the Le Chatelier's principle, it means if the stress is an increase of a substance, the shift will be away from that substance. Why? Because extra concentration needs to be used up. Okay, so basically let's give an example. So A plus B is equals to C. Remember, it's a balanced, it's a equilibrium. So when the system is at equilibrium, if we increase C, it means the system will shift towards the reverse reaction or the backward reaction in order to reduce the concentration of C. So that's what we mean. So if you increase, let's say you reduce A, decrease the concentration of substance, the shift will be towards that side. So if you reduce A, it means the reaction will also move towards the formation of A in order to replace the A that has been removed, so that it can reach a new equilibrium. So it needs to produce more substance to make up of what was removed. So that's what we mean. So if you increase pressure, let's say B is a gas. If you increase pressure, which means pressure, it mainly affects gases. So in order to relieve the pressure, it will reduce the substance that is a gas in order to reduce the volume. So if you increase the pressure, the forward reaction will be favored in order to reduce B. So increase of the pressure in a system towards fewer moles of gas. So it will favor the side of a reaction where there are fewer moles of gas. So, because in some cases, for example, let me say we have got X, which is a gas, to form Y, which is a gas, and Z, which is a gas. So if you increase the pressure, it means it favors the backward reaction because there is only one mole of gas here, as opposed to the forward, which has got 2 moles of gases. So that's what we mean. So if you decrease the pressure, it will favor the formation of gases. So it means if you reduce the pressure, it will favor the forward in order to compensate for that decrease in pressure. So increase in temperature of a system, it means if you are increasing the temperature, it will favor the reaction that will absorb, which means the exothermic. So if you decrease the pressure, the shift will be towards exothermic reaction if is favored, which means more heat will be released to the system in order to compensate for the decrease in temperature. So more heat or energy needs to be produced to make up for the loss. So if we add a catalyst, there is no shift, because a catalyst does not affect anything, it only reduces the activation energy. So the rates of the forward and backward reaction are increased by the same amount. So a catalyst, it just increases both the forward and the backward reaction. In other words, it just makes it reach that state much faster in terms of time. So this is basically what you need to know for the Chatelier principle. But for more practice questions, will be covered on our website and exam preparation. So if you like this content, please click the like button and subscribe to our channel not to miss any new information. If you have any questions, you can put them in the comment section below or use our email on the right, so that we can attend to you the best way we can. So thank you for watching. Have a great day. Bye bye.